Welcome to The Explainer. Let's just dive right in today. Picture for a second a massive offshore oil platform sitting right in the middle of the unforgiving North Sea. Now, if you've ever seen photos of these megastructures, you know they look absolutely overwhelming. It's just a dense jungle of metal, with pipes of all sizes running in literally every conceivable direction. But here's the secret. Not a single inch of that piping is random. It's an intricate, highly pressurized circulatory system. So today, we're going to look at the incredible engineering and the microscopic precision required to actually build that system. We're going to track the journey of one of the absolute fundamental building blocks of offshore construction, and that is the pipe spool.
Here's our roadmap for today's explainer. We're covering the prefabrication strategy, offshore welding processes, hunting for microscopic defects, the traceability paper trail, and finally, offshore assembly. Let's get to it.
Section 1. The prefabrication strategy. Building safely on dry land.
Okay, to understand how we build these things, we really have to look at the core engineering problem. You might think that when building an offshore platform, you just send a bunch of welders out into the middle of the ocean to weld all the pipes together right there on the deck, but no way, we definitely don't do that. Doing all this welding in situ, which just means on-site, offshore, would be enormously expensive. It'd be incredibly time-consuming, and you'd be fighting hostile weather, rocking vessels, and corrosive salt spray the whole time. It's a nightmare. So instead, the logical solution is workshop prefabrication. We keep the work in a highly controlled onshore environment where fabrication is super efficient and, most importantly, where we can maintain rigorous, absolute quality control.
So what exactly is a pipe spool? Well, it's a pre-assembled, single length of pipe, usually with flanged ends, that is fabricated entirely in a workshop before ever being transported offshore. Honestly, think of it like a giant, high-stakes Lego brick. By breaking this massive process piping system down into these modular, manageable spool pieces, we make offshore construction entirely possible.
Section 2. Offshore welding processes. Joining the steel.
Let's step inside that onshore fabrication workshop for a minute. Here, the raw steel pipe is cut, the edges get beveled, and the pieces are carefully fitted up. But I really want you to consider the immense stakes here. How do we guarantee a perfect joint that can actually withstand extreme hydrocarbon pressure? Because remember, these lines are carrying crude oil, gas, and condensate. If a weld fails on a water line, sure, you get a puddle. But if a weld fails on a high-pressure hydrocarbon line, you release a flammable cloud that can literally turn the entire pipe into a bomb. So perfection isn't just a goal here, it's an absolute requirement. To hit that level of perfection, fabrication shops use very specific, highly controlled welding processes. First up, we've got TIG welding, or gas tungsten arc welding. Now, this is relatively slow, but the quality is unmatched. It's generally used for the root pass, that absolutely crucial first pass that penetrates the joint, and also for small bore or stainless steel piping. Next, to build up the thickness of the weld, they might switch over to MMA or SMAW, which you probably know as stick welding. It's super flexible and versatile, making it perfect for the fill and cap passes on carbon steel. And finally, for high-volume, highly consistent results, especially when we're talking about subsea flow lines or stainless steel, we use automatic orbital welding. This is so cool. The torch literally rotates around the pipe entirely on its own, delivering a flawless, machine-perfect weld every single time.
Section 3. Hunting for microscopic defects. Non-destructive examination, or NDE. Okay, so we've welded the spool. Now we have to prove that weld is completely flawless, and we have to do it without breaking it apart to check, so we shift from the macro scale of welding to the micro scale of defect hunting. Depending on how critical the pipe is, sometimes up to 100% of the butt welds have to be examined. Let's break down the 4 main methods here. Notice how the top 2 deal with deep, volumetric defects. Radiographic testing, or RT, uses literal X-rays to see straight through the weld, revealing deep, internal flaws like tiny gas bubbles, which we call porosity, or trapped slag. Then there's ultrasonic testing, or UT. That uses high-frequency sound waves that actually bounce off internal defects. The modern phased array systems can even generate highly detailed cross-sectional images of the weld. Then we shift to surface techniques. Magnetic particle inspection, or MPI, applies a magnetic field to carbon steel. If there's a surface crack, iron filings or UV fluorescent particles will gather right along that invisible fault line. And finally, dye penetrant inspection, or DPI, uses this brightly colored dye that gets drawn into microscopic surface-breaking cracks by capillary action, and then a developer pulls it back out to make it totally visible. It is literally microscopic detective work.
Section 4. The traceability paper trail. Tracking every detail.
So, we built the spool and we proved it's perfect.
But in offshore engineering, a perfect weld just isn't enough on its own. You need permanent, undeniable proof to build a continuous chain of evidence. So every completed spool gets a unique identifier tag. From that single tag, which is step 1, you can trace backwards through time. Step 2, you pull the exact NDE and inspection reports for every single weld on that specific piece of pipe. Step 3, you can see exactly which welder did the work, what welding procedure they used, and even what specific electrodes were consumed. And this goes all the way back to step 4, the mill certificates. These documents prove the exact chemical composition and mechanical properties of the raw steel, straight from the steel mill where the pipe was first forged.
Now, why does all this paperwork matter? Well, it's not just about passing some initial inspection. Imagine it's 20 years down the line, and that pipe spool has been taking an absolute beating from a highly pressurized, slightly sour hydrocarbon mix. If engineers need to make a repair or modification, they can't just guess what kind of steel it is or how it was welded. They have to know exactly what materials and processes were originally used to ensure that any new welding doesn't trigger a catastrophic metallurgical failure. Traceability is literally the foundation of long-term safety.
Section 5. Final offshore assembly, putting the puzzle together.
All right, our spool is built, inspected, heavily documented, and now it's finally time to load it onto a vessel and head out to the offshore platform. When these prefabricated spools are craned into the tight, congested spaces of an offshore module, they have to be connected up to vessels and other equipment. Notice how they're bolted together using flange joints. See, even with the absolute best 3D modeling in the world, you just can't guarantee that a pipe spool and a giant pressure vessel nozzle will line up perfectly to the exact millimeter out in the middle of the ocean. Flange joints give the installation team tolerances. They give them wiggle room. If things are just slightly off, they can adjust the joint using gasket shims to ensure a perfect, stress-free fit without ever having to attempt a highly dangerous field weld.
But bolting a flange is a complete science in itself. Flange integrity is a massive focus out there because a leaking flange is a huge source of offshore hydrocarbon releases. The gaskets have to be perfectly specified for the fluid and the pressure, the flanges have to be perfectly aligned, and the bolts, they're tightened using a specialized hydraulic torque machine. Just pounding a wrench with a hammer is strictly a last resort. And it's a Goldilocks situation. If you under-torque the bolts, the pressure just pushes the fluid right past the gasket. But if you over-torque them, you can actually crush the gasket, damage the flange faces, and ironically, create a critical leak anyway. Precision is literally everything here.
Once the whole system is finally bolted together, it is testing time, and this happens in 2 critical phases. First up is the hydrostatic strength test. They literally fill the entire system with water and pump it up to 1.5 times the design pressure. Now, why water? Because water doesn't compress. If a weld somehow fails under that massive pressure, the pipe just cracks and trips water. It doesn't explode. So this proves the structural integrity. But water isn't going to find every microscopic gap. So after the water is completely drained, they perform a pneumatic leak test. They use nitrogen at a much lower pressure to verify those final installed flange connections.
This final commissioning step is really the last line of defense. Often, they'll mix just a trace amount of helium into that nitrogen gas. Helium atoms are incredibly tiny. Technicians will literally walk around the platform and sniff every single flanged connection with a highly sensitive sensor. If there's even the slightest leak path, the helium will find it. And this absolutely has to be verified before a single drop of volatile oil or gas is ever allowed to flow through the system.
So we've traced the entire journey, from a raw piece of steel pipe in an onshore workshop, through meticulous welding and microscopic X-rays, across a massive paper trail of traceability, all the way to a bolted, pressure-tested flange sitting out in the middle of the ocean. The next time you see a picture of a massive offshore platform, don't just look at the overall size of the thing. Look a little closer at the piping. Ask yourself, how many perfectly tracked, micro-inspected pipe spools are working together right at that moment, silently holding back immense pressure just to keep that entire structure from failing? It truly is a hidden triumph of engineering. Thanks so much for joining me in this explainer, and keep asking those great questions.